We often think of space, between the galaxies as just empty, vast, dark nothingness.
Right. That's the common picture.
But what if that nothingness isn't empty at all? What if it has this hidden structure, like a network connecting everything?
Ah, you're talking about the cosmic web.
Mm-hmm.
And yeah, that's exactly it. It's less of a void and more like this gigantic, mostly invisible scaffolding stretching across the entire universe.
Scaffolding. Made of what?
Well, mostly dark matter, that mysterious stuff, but also regular gas and even galaxies themselves, all woven into this incredible, immense pattern.
Okay, and that's where our sources come in today. We've been looking through a bunch of articles, Earth.com, Telescope Live, Science X, stuff from Keck Observatory, ESO.
The Max Planck Institute, Live Science, Astronomy Magazine, too. Yeah, quite a collection.
And they're all buzzing about some, frankly, amazing new ways we're actually seeing this cosmic web.
They really are. There are two big discoveries we should probably focus on. One gives us this incredibly sharp picture of a filament, like a thread in the web, way back in the early universe. And the other one, a team stumbled upon a really distinct filament, surprisingly, much closer to home, kind of in our cosmic neighborhood.
Right. So our mission for this deep dive is to unpack that. What is this cosmic web, really? Why are these new observations such a big deal?
And what do they tell us about, how everything formed? Galaxies, stars, the whole structure of the universe.
Exactly. We want to get to those aha moments for you, hopefully without making your head spin with too much jargon.
Sounds like a plan. Where should we start?
Let's start with the basics. This cosmic web. What exactly is it structuring?
Okay, so imagine the universe on the absolute largest scale. It's not just galaxies scattered randomly. There's an architecture. The cosmic web is that architecture.
Right.
It's this network. Think threads or filaments connecting at intersections, which we call nodes.
And these filaments are made of?
Primarily dark matter.
Right.
About 85% of all matter is dark matter. And it basically provides the gravitational backbone. It's the invisible framework that shapes these huge structures.
So dark matter carves out the paths, essentially.
Precisely. And then ordinary matter, mostly gas hydrogen and helium, gets drawn in by gravity and flows along these dark matter filaments.
Like rivers of gas flowing through space.
That's a great analogy, yeah. And where these filaments meet, at the nodes, the density gets really high, and that's where galaxies tend to form and cluster together.
Ah, okay. So the web isn't just structure, it's also the delivery system for galaxy fuel.
Exactly. These filaments are the cosmic highways connecting galaxies and even whole clusters of galaxies. It all forms this vast, interconnected tapestry.
It sounds incredible, but also faint. Hard to see if it's mostly dark matter and diffuse gas.
That's been the huge challenge, yes. Directly imaging the gas in these filaments is incredibly difficult because it emits very, very little light.
So how did we study it before?
Mostly indirectly. We look at very distant, bright objects like quasars if their light passed through a filament on its way to us.
The gas in the filament would absorb some specific colors of that light, like leaving a shadow.
Exactly like leaving a shadow, or more accurately, an absorption line in the spectrum. We knew something was there because it blocked the light, but we couldn't really see the filament itself emitting light.
Okay, that makes this first big discovery we talked about even more impressive than this high-definition image. Tell us about that.
Right. This was a huge effort by an international team using an instrument called MUSE.
MUS.
Yep. It's on the Very Large Telescope, the VLT, down in Chile. And the key thing here was the sheer amount of time they dedicated. Hundreds of hours.
Hundreds of hours just staring at one tiny spot in the sky.
You got it. Just relentless observation.
Wow. What did they manage to capture?
They got the sharpest, clearest image ever taken of a cosmic filament emitting its own light. And this thing is enormous. It stretches about 3 million light years across.
3 million light years.
And it's connecting two galaxies that were furiously forming stars way back when the universe was only about 2 billion years old.
So we're seeing it as it was almost 12 billion years ago, peeking into the universe's youth.
Exactly. It's a snapshot from a very early, very active period.
What's the really groundbreaking part of seeing it so clearly?
For the first time, they could directly trace the boundary. They could see where the gas inside the galaxy stopped, and the gas belonging to the filament itself began. And crucially, they did this by measuring the actual light emitted by the hydrogen gas in the filament, faint as it was.
Not just its shadow, but its own faint glow. That is a leap. So we're seeing the connection, the supply line.
Precisely. It gives us this direct view of how gas flows from the intergalactic medium through the cosmic web and presumably funnels into galaxies to fuel star birth. It's like finally seeing the pipes of the universe's plumbing system.
Amazing. And did this picture match what our theories predicted, our simulations?
It did. Remarkably well, actually. Researchers at the Max Planck Institute for Astrophysics ran these incredibly detailed supercomputer simulations based on our standard model of cosmology. And when they compared the simulation results for how gas should be distributed in such a filament with the actual MUSE image, they found really substantial agreement.
That must have been a relief. So theory and observation are holding hands here.
Absolutely. It's a powerful confirmation that our understanding of how structure forms and how gas behaves on these large scales is fundamentally on the right track.
What does this open up now? Being able to see these ancient structures.
It opens up whole new avenues for studying that really thin, diffuse gas environment around galaxies. Understanding where their fuel comes from, how it gets there, especially in the early universe when galaxy building was in overdrive, is a major step.
Okay, so that's looking deep into the past. Now, let's switch gears to this other discovery, the one closer home, the local filament found by chance.
Yeah, this one's fascinating too, partly because it was unexpected. A team led by Mariam Arab Salmani was actually just studying the area around a particular galaxy, relatively nearby, cosmically speaking.
How nearby is nearby?
About 5 megaparsecs away. Still a huge distance, obviously,
Yeah.
but definitely in what we'd call our local universe compared to the MUSE filament.
Okay. And they just stumbled upon something.
They noticed this really peculiar alignment, an almost perfectly straight line of 8 galaxies.
A straight line of galaxies. That seems unlikely to be random.
Exactly. So they looked closer, specifically at their redshifts.
Redshift tells us how fast things are moving away from us due to the universe's expansion.
Right. And all 8 galaxies had very, very similar redshifts. That suggested they weren't just randomly placed, but were likely moving together, bound within some larger structure.
A filament.
That was the suspicion. So they pointed the Jansky, a very large array, the JVLA, a powerful radio telescope at that region, to look for cold hydrogen gas, what astronomers call HI.
Did they find gas along the line?
They did. They detected 12 new sources of HI gas right along that suspected filament.
Yeah.
And crucially, these gas clouds also had similar redshifts to the galaxies.
12 more clues. That sounds like strong evidence for a filament connecting them all.
It certainly pointed that way. But then came another twist. They followed up with optical observations using the Canada-France-Hawaii telescope.
To see if these gas clouds were actually inside galaxies?
Exactly. And they found that only one of the 12 HI sources was associated with a visible galaxy, the other 11. They seemed to be just clouds of hydrogen gas, no stars detected.
Wait, just gas clouds? Floating in the filament? Not galaxies?
Apparently so. Dark gas clouds.
Is that normal? Have we seen that before?
It's potentially the first direct observational evidence of such things. Dark gas clouds residing within a cosmic filament. It's quite novel.
What does that imply? Are these like failed galaxies or something else?
Well, when they looked at the radio signals from these clouds, the HI spectral lines were broader than you typically see from gas in a stable galaxy disk.
Broader lines mean?
It suggests the gas inside these clouds is moving around quite intensely, maybe turbulently. It hasn't settled down or virialized, as astronomers say. It fits the picture of gas still flowing and churning within the filament, not yet collapsed into stars.
So maybe not a smooth river of gas, but more like clumps or eddies moving along the filament highway.
That's the interpretation the researchers favor. These clouds might be denser peaks within a more complex gas flow along the filament.
Okay, that paints a different picture of filaments than just smooth streams. How does this fit with the big cosmological models? Do simulations predict thin filaments with dark gas clouds?
That's a key question. They compared their find to the Millennium TNG simulations, huge computational models of the universe. They found that filaments this thin and straight are pretty rare in the simulations, maybe around 4% or so. But importantly, they do exist in the model.
So unusual, but not impossible within our standard understanding, lambda CDM.
Exactly. It doesn't break the model, but it certainly highlights a type of structure that might be more common or detectable than we thought.
What's the big significance of finding this local, potentially clumpy filament with dark gas clouds?
It gives us a really valuable close-up look at the composition and the dynamics of these structures right now in our cosmic era. It hints that filaments might harbor these significant reservoirs of cool, dark gas.
Gas that could potentially fuel galaxies later on.
Potentially, yes.
Yeah.
Or maybe it tells us something about how gas gets processed or stripped within these environments. It adds a new layer of complexity to the cosmic web picture.
So these two studies, one looking far back, one looking closer, they really complement each other, don't they?
Absolutely. They both showcase how much our ability to directly see the web is improving thanks to incredibly powerful instruments like MUSE for optical light and the JVLA for radio waves.
One shows the web-feeding galaxies in the early universe.
And the other gives us hints about the state of the gas within filaments in the more recent universe, maybe revealing these hidden gas clouds.
And underpinning both is still the idea of dark matter, right? That invisible scaffolding we started with.
Definitely. Dark matter's gravity is the engine driving the formation of these filaments in the first place, gathering the ordinary matter into these structures. These observations fit perfectly within that framework and help us refine the details.
So where do we go from here? Just find more filaments.
That's a big part of it, yeah.
Yeah.
Both teams stressed the need for more observations, deeper surveys. The goal is to map out more of these structures, both near and far, to really build up a comprehensive census of how gas is distributed across the web and how that connects to galaxy evolution over all of cosmic time.
You mentioned MUS earlier, and it sounds like it was absolutely key for that high-definition image of the distant filament. Can we dig into that a bit? What makes MUS so special for this kind of observation?
Sure. MUS stands for Multi-Unit Spectroscopic Explorer. It's mounted on one of the VLT's giant telescopes in Chile. Its big advantage is that it's an integral field spectrograph, or IFS.
Integral field.
Meaning that for every single pixel in its view, it doesn't just record brightness, it records a full spectrum of light. It breaks the light down into its component colors or wavelengths.
Ah, okay, so it's like getting thousands of spectra all at once across an image.
Exactly. It combines imaging with spectroscopy over a relatively wide field of view. MUSE itself actually chops the field into 24 smaller segments, and each segment is fed into its own spectrograph unit.
Clever.
Yeah, it's incredibly efficient. And crucially for the cosmic web, it has very high sensitivity, especially in the visible light range where that faint hydrogen glow appears. It can also use adaptive optics to counteract the blurring effect of Earth's atmosphere, giving really sharp images.
So wide view, high sensitivity, and the ability to get spectra everywhere. That sounds tailor-made for hunting faint, extended things like filaments.
It really is.
Yeah.
That ability to detect incredibly faint emission over a wide area, like the light from that 12-billion-year-old filament gas, was something we just couldn't do effectively before MUS came along. It's been revolutionary for this field.
Okay, great. Let's try and wrap this up then. If you had to boil it down, what are the absolute key takeaways from this deep dive into the cosmic web?
I think the main thing is that we've moved beyond just inferring the cosmic web exists to actually seeing its components directly. We're imaging the filaments.
The backbone of the universe.
Right, and we're seeing how these filaments act like cosmic rivers, channeling gas across immense distances and time to feed galaxies. And we're getting this richer picture by looking both far away into the early universe and nearby, revealing potentially different aspects like those dark gas clouds.
So for you listening, why should this matter? What's the big aha moment here, beyond just cool space pictures?
The aha moment, I think, is grasping that the universe isn't just islands of galaxies in an empty ocean. It's fundamentally interconnected, that empty space has structure, purpose, and it's directly responsible for building the galaxies we see, including our own Milky Way.
It changes your whole perspective on the night sky, doesn't it? Realizing it's all part of this vast, mostly invisible web.
It really does. It underscores the interconnectedness of everything on the grandest scale imaginable.
Okay, so final thought then. Something provocative for us to chew on.
Well, it's amazing that these observations confirm our models so well. That's a huge win for cosmology. But like any good science, answering one question opens up so many more. What else is hiding in these filaments? We found potential dark gas clouds. Are there other unexpected components? How exactly did these filaments evolve? Did they all look the same, or is there huge variety? And what will the next generation of telescopes, like the extremely large telescope or the square kilometer array, reveal about these faintest, largest structures?
We've peeled back one layer, but you get the sense there's still so much more hidden complexity in that cosmic web waiting to be untangled. What secrets are locked away in those dark gas clouds about how matter itself evolves? It really makes you ponder the sheer scale and maybe the ultimate fate of this interconnected cosmos.